So let me just first start by thanking the organizers, Livia and the rest, for having considered me and given me the opportunity to talk today. So it's my great pleasure to be back here. It's Nottingham is where I started, so it's good to be back where I started. So as the title today suggests, I'm going to be talking about K-stability of certain Fano varieties, in particular del Pezzo surfaces, which have certain singularities. So I will go with just the flow of the way the talk is going to go. So the first thing would be I will be introducing what K-stability is in a very rough sense and why we care. So this is just why do we want to study this at all? And then I will follow this by then giving you an idea of the objects of interest for us today, which are basically del Pezzo surfaces, but then they are very special in the sense that I'm looking at quasi-smooth, well-formed hypersurfaces in weighted projective space. I will tell you why these are del Pezzo surfaces and why they are singular and what sort of singularities they are and so on. So I will introduce what the objects of interest are. Followed by K-stability itself and the sort of obstructions we have. So first, the obstructions we have to showing that they are not K-poly stable. This is the easy way out, but of course, most of them do not satisfy any of these obstructions for you to just conclude. But they do exist. So we have certain obstructions. And then I will also tell you certain invariants that you can use to compute very explicitly and see whether it is K-stable, K-poly stable, and so on. So these are alpha invariant, beta, and the delta. My idea is today to give you the definitions of these and then to actually explicitly show you computations for all the three of them, provided time permits. So this is where we'll go. And then we do the actual examples. So I will be doing one index 2 hypersurface. I will tell you what indices are. And I think two more examples. 2 examples of index 3. Again, if time permits, this is. And then I will tell you where we are going with the future. So where are we headed now? And what are we working on? Okay, so let me start. So K-stability. So this was something that was originally introduced by Tian, introduced by G. Tian. And the motivation was basically in a complex geometric sense to understand the existence of Kahler-Einstein metrics. So I will tell you why we can go back and forth in case of Fanos, but this was the motivation behind even introducing the concept of K-stability. And in the case of Fano varieties, there was a huge breakthrough because of the following conjecture. So we have the Yau-Tian-Donaldson conjecture, which basically states that if you take any Fano variety, say X, it has the Kahler-Einstein metric if and only if X is K-poly stable. So I should say one thing. So K-stability initially was introduced using something called generalized Futaki invariance. So we had the Donaldson-Futaki invariant with which you could define what K-stability is, K-poly stability, and K-semi-stability. But then, so this conjecture tells you that you could go back and forth. So if you want to understand the existence of a metric, the Kahler-Einstein metric, it's enough to show that it is K-poly stable and vice versa. And so the breakthrough here is that Yau-Tian-Donaldson and Sun, I think Tian too, proved the Yau-Tian-Donaldson conjecture for smooth Fanos. For smooth Fano varieties. And this was followed by Lee, Wong, Zhu, Berman, Spotty, Sun, and Yao. It's a lot of people, all of them contributing towards proving this for TLT Fanos, which is our case, which is exactly why we will be moving back and forth between proving case stability and just understanding existence, because this works for us. Our objects of interest are going to be KLT Fano del Pezzo surfaces, so KLT surfaces basically. So this is pretty much why we bother from a complex geometric sense to understand the existence of the metric, and so you can go back and forth. Having said this, now let me go on to then introducing the actual objects of today. Today I'm going to be dealing with quasi-smooth, well-formed hypersurfaces in a weighted projective space. And so these are basically surfaces with the form SD in weighted projective space with 4 weights. So of course this is of dimension 3, and then you have a surface there. And I want the weights to be ordered. Now I will briefly tell you what each one of these are, so you have an idea. So when I say quasi-smooth, what do I mean? So basically this means that when I take the affine patches in the surface, it's only singular at the origin. I will explain this. So singular only at the origin in C4. So what do I mean by this? So for every x that you have, for every s that you have, you can look at just the affine space, and so you have the canonical projection for any projective space. And so once you do this, you can look at what is called the affine cone, which I mean you can refer to this as this. I mean it's just a notation, but it's called the affine cone. And so once you look at this, the way you projectivize this is there is a C star action on it. There is a C star action on your affine cone. And so the singularities on this affine cone is, so when you look at your surface S, this is nothing but the quotient by your action, because you're projectivizing it. So the only singularities you can have on your surface that you start off with are going to be given by your C star action. And so this is exactly why your surface can have at most cyclic quotient singularities. So this is our setup. Okay. And by a result of Kola, we can then write down what our canonical or anti-canonical is. And this is nothing but the sum of your weights minus the degree. So D is the degree of my surface S. So I should say that, so this degree, when I say D is the degree of the surface, I just mean that S is given by a polynomial of these weights. So it's quasi-homogeneous. So it's homogeneous with respect to the weights given. And so F is of degree D with respect to the weights. That's what I mean when I say the surface is of degree D. So from a result of Kahler, we know that the anti-canonical can be given this way. And so if you look at this number, and you always assume that it is positive, then you know your minus KSD is ample, which is the case of a Fano. And this is exactly what we're going to do. This is what we call the index of the hypersurface. And we always assume this. So in our setup, our I is always greater than 0. So we know the anti-canonical is always ample. And so we are looking at Fanos. And because it's a surface, it's a Fano surface. So that's a del Pezzo surface. And as I had shown before, you can only have cyclic quotient singularities. So this is our setup. This is the sort of singularities we are going to have on our hypersurface. So this is it being quasi-smooth. What does it mean for it to be well formed? So when I say SD in P, when I write this, I always mean P with these weights. So when I want SD to be well formed, so SD is well formed if it satisfies two conditions. So one, P itself is well formed. This only means that when you take any three weights, so you take A1, A2, A3, A0, A2, A3, and so on. So take any of the three weights out of the four, and the GCD should always be 1. So this is what it means for P, your weighted projective space to be well formed. So you want P to be well formed, but also when you do not want any codimension 2 singular strata of P to be in SD. So this only means in our case that we do not want any singular curve of your weighted projective space to be in your surface. So in particular, your singularities of your surface are just going to be points. They're going to be isolated singularities. So this is our setup. We have quasi-smooth, well-formed hypersurfaces in weighted projective space. What do we already know about them? So one of the main questions once we have this setup is the classification problem. So suppose you want a surface with these with these weights with this particular degree, and all that you are imposing is the condition that I want my I to be positive. So then the question then becomes, describe all possible such surfaces that can exist. So basically it means that you're not exactly fixing the weights or the degree, but you're just saying, okay, I need this to be satisfied. For different values of I, what all surfaces can I have with what all weights? So this was first solved by Johnson and Kahler for I equals 1. So if I'm not mistaken, this is in 2001. So we have a complete classification for I is equal to 1 given by them. Which is then followed by for I equals 2. We have now, so I can maybe then tell you for I greater than or equal to 2, we have the complete list by Eric, which basically uses a computer code to then give you the infinite series for all possible indices that you can have. So now we have a complete list of all possible such 5 tuples that you can have. yeah, so for indices greater than or equal to 2. So we have all of this now. So now I thought I would then come out, okay, if we want to understand case stability of them, what tools do we have in hand? So the first thing is, what sort of obstructions do we have? So this was first, so one of the first obstructions is by Gauntlet, Martelli, Sparks, and Yau, which basically says that your X, be it any Fano variety, so in particular, so let's maybe set this up. So I'm generalizing and giving you a general obstruction, as long as it's just a hypersurface in weighted projective space. So so this is any Fano of this sort, and this is basically telling me that X admits no Kahler-Einstein metric if either one of them is satisfied. So either your I, which is the index, again, index being the sum of the weights minus your degree, your index being greater than NA0, or if the degree times the index to the power of n is greater than n to the power of n, the product of all the weights. So this was one of the first obstructions that we have that tells you, okay, it's not K-polystable. But this was improved by Chelsov and Shramov in the sense that they prove that these two inequalities are not independent, and that if one was satisfied, the other was just an implication. So if you have the weights ordered as are set up, and you have the degree, as long as this was satisfied, so you had I from 0 to n minus d to the power of n greater than n. So this is in a much general setting. You don't even need it to be a Fano or a weighted projective space or any of it. So as long as you had these numbers, which were positive real numbers ordered in a particular way, as long as this was satisfied, this would then imply that my I from 0 to n minus d was always greater than n A0. So if you look at it here, it's basically, if I said this to be my I, which is what we had in our setup, it's telling you that as long as this is satisfied, it implies this. So they basically prove that these two inequalities are not independent. But it's still an obstruction. So as long as you have any one of these, you still have that it doesn't have a Kahler-Einstein metric. So in our case, what does it mean? So in our scenario, my n is 3. So the obstruction basically tells me that my SB has no Kahler-Einstein metric if my I is greater than 3 A0. Or the other one, so DI cube being greater than 27 times the product of the weights. So we have this obstruction, which you can use to show that few hypersurfaces don't fall, they don't have the Kahler-Einstein metric. But we also have another one. But before I even give you that, let me tell you what the Tian's criterion is to prove the existence of the metric. So Tian's criterion to show existence of Kahler-Einstein metric. So this basically states that you have X to be a Fano variety. X admits a Kahler-Einstein metric if my log canonical threshold of X was greater than dimension of X by dimension of X plus 1. And just to tell you what the log canonical threshold is, this is the supremum of all lambdas such that the pair x comma lambda d is log canonical for any d, which was just numerically minus k. Basically d being any effective Q divisor. So we have this given by Tian. So in our case, let me say, so because the dimension is 2, we just need LCT of x to be greater than 2/3. And if this works, then we know that it admits a Kahler-Einstein metric. So this could be used too, and this has been used in a lot of cases, which I will tell you in what cases they have been used. So this is a criterion to then say, okay, when do we know that it admits a Kahler-Einstein metric? But this also gives an obstruction in a sense, because, so in our case, remember that in our case, SD is in P A0, A1, A2, A3, and my index being the sum of the weights minus my degree. So this only means that my anti-canonical is given by some hyperplane. So I can say hx being x equals 0. The reason this is true is it's I times a hyperplane, but the hyperplane has weight A0, and so it's the same as saying I over A0 times the hyperplane, which is given by x equals 0. If this was my x, y, z, t. And so when I look at LCT of x comma d, and this is nothing but where my d is just anything that's numerically equal to minus k, I'm looking at something of the form I over A0 hx. And so this, by the definition of it being log canonical, so x comma d being log canonical, this immediately implies that I need my I over A0 to be less than or equal to 1. So the best way to do this would be, okay, you look at this if you want to understand the threshold, and so you know your lambda, your threshold has to be at least A0 over I. So this tells you that the LCT of your x comma d is at the most A0 over I in our case. So this immediately gives you an obstruction, because if your I, so if my index was greater than or equal to 3A0 over I, 3A0 over 2, this is telling me that my LCT of x comma d is less than or equal to A0 over I, which will in turn would be less than 2 over 3. So you cannot use Tian's criterion anymore if this holds, which was the reason why I even introduced. So we want to look at cases where I is less than 3A0 over 2 to use Tian's, because otherwise you cannot. So you immediately know that if your index is already greater than or equal to 3A0 over 2, you need to use some other means to then figure out if it has a Kahler-Einstein metric at all. So this is another thing that I thought might be interesting to know for anybody who wants to do these computations. So now, let me now introduce the invariants that I will need to do some examples. So again, recall. So this is my invariance. I've already, this is exactly what alpha is, by the way. So this is my alpha of x. So this is the alpha invariant of Tian. But okay, so I will then give you what my beta and delta invariants are. So recall our setup. You have a del Pezzo surface with KLT singularities. And suppose you have, say, a birational morphism such that E is a prime divisor in S tilde. Okay, so with this we have two different things that we can define. So first is called the log discrepancy, which is basically 1 plus the order along E of the relative canonical. So this is one thing, and the other one that we will need to do the computations is this. So this is 1 over minus ks square 0 to something called the threshold. So that's the pseudo-effective threshold, which I will define. I will tell you what it is. Volume of the divisor that we have. So there are two things here which may not look too familiar. So what is my tau v? This is called the pseudo-effective threshold. And you can define this by saying, okay, it's the supremum of all the u's such that my divisor that I'm looking at is big or pseudo-effective. In this case, it's the same thing. Okay, so this is one thing that might not have been familiar, and volume. So I thought it might be useful to just give you certain properties of the volume that we will need to do certain computations. So when you say volume of the first thing, when you say volume of a divisor, this is strictly greater than 0 if and only if my divisor is big. So when I say D is, say, an effective divisor. And the second is if my D is nef, then my volume of D is basically just the top self-intersection of my divisor. So where n is the dimension of the x that you start with. Another thing that we would need is if in case your D was in F, what do you do? So you have something called the Zariski decomposition in the case of surfaces, where when you say D is just any pseudo-effective divisor on our surface, say if you're looking at surface S, then you can write this as a positive and a negative part and split it with, so this is called the positive part and this is called the negative part, which with certain properties. So the positive part is nef, and the negative part is, say, with certain curves, but it has to be still effective. And the intersection matrix of the negative part has to be negative definite. And the third property is the curves in this case, which form a part of your negative part, has to then intersect your positive part by 0. So it has to be orthogonal to your positive part for every I. So why do we do this? So once you do this, we have a result that says, okay, the volume of D is nothing but the volume of just the positive part, because that's the nef part, and that's nothing but P square because the dimension of what we are looking at is 2. But basically it's from here. So we will need these properties to then go on and do the actual computations. But the idea is once we define these two, log discrepancy and the S, we can have two different invariants. So the first one is the beta invariant. So the way the definition goes is if you take E, where E is the prime divisor over our surface S, beta of E is given by A S of E minus, so the two things that we had defined right above. And why does this help us? So the theorem, this was given by Fujita and Lee independently, and of course contribution of Bloom and Zhu as well, that says that X is case stable if and only if my beta of E is greater than 0 for every prime divisor E over S. So you need to do this for every prime divisor E over S. And this next is that X is case semi-stable if and only if beta of E is greater than or equal to 0, again with the same implication. So this is one invariant, and the other one that we will be using is the delta invariant, which is defined by, so delta of S is given by the infimum of E over every, infimum taken over all the prime divisors over S, where it's the quotient of the total. And why do we care again with this? Because this is now given by Bloom, Johnson, Fujita, Lee, Liu, Zhu, and Zhuang. I think I haven't missed anybody, but hopefully I've mentioned all of them here. So as long as delta of S is greater than or equal to 1, then you know S is case semi-stable. If my delta of S is greater than 1, then I know my S is case stable. So I should say something because I keep going between case stability, case semi, and K polystability. So the implications are that case stability is the strongest, but this would immediately imply K polystability, which in turn implies K semi-stability. So K semi-stability being the weakest. Okay, so we have all of these invariants to do the computations with. But one more thing that would actually help us is a local analog of the delta. So if you take a point P on your surface, I can define something called a delta P, which is given by this, where as long as P is in the center, where my E is above over S, we can have a local definition of delta, and then in turn your delta S is given by the infimum over all these points of all the delta P's. So why does this help? Because with a very recent theory of Aban and Zhuang, we have a very nice way of computing Zhuang theory. So we have a very nice way of computing delta P very explicitly. And this in turn gives you delta, and so you can understand K stability. So this is the last formula, I promise. So this is del Pezzo surface again. So we are still in our setup. The setup is still the same with at most KLT, which is exactly what we have. Say Y is an irreducible curve on our surface. So then you can define, you can estimate delta P. So this is the theorem by Aban Zhuang, which was then later improvised and then came up with this inequality by in the book that's written by, I'm going to write just the surname. So the first letter of every surname. So this is Araujo, Chelsov, Anna Maria Castravit, and then we have Fujita, and then Anna Sophie, and then we have Jesus Martinez Garcia, Shramov, Suz, and myself. So where we say, okay, it's given by the estimate of the minimum of this being exactly what I had defined above, and also given by the log discrepancy of the point in the curve, and a very funny number. Now this funny number can then be given by this, which is 2 over your minus ks square, 0 to again your pseudo effective threshold, h of u du, where I say h of u is the positive part intersected with the curve that you start with, and then the order of the negative at the point, plus the volume, then it's just restricted to the curve. So this is just formulae right now, but maybe you'll get a better understanding of it when you do an example, which is exactly what I'm going to do next. So do we have any questions until now? I never stopped to ask.
So for now, nothing has come up.
Could you scroll up a little bit? Thank you. Yeah, I wanted to see what's in the minimum. Thank you.
Okay. Okay, so the next part, what I thought I would say is, what do we know about the indices as of now? So we have worked with index 2 and 3, but what do we know about index 1? So in the case of index 1, is it okay if I scroll up now?
Yes.
Yeah. Okay, so for index 1, so what do we know? That's the next part. What do we know? So in the case of index 1, by the works of many, Johnson, Kolar, Rauho, Chelsov, Park, and Shramov, just because of lack of time, I'm just going with the first letters. So because of the work of all of these people, we have that for I equals 1, except in the case of one particular hypersurface with a very specific restriction. So with the monomial yzt not being in the polynomial that defines your S. So if this wasn't true, except in this case, they proved that alpha was greater than 2/3, and therefore that exists a Kahler-Einstein metric. And then the reason why there's an exception is, of course, you can guess it, the alpha here is less than 2/3. That's strictly less than 2/3. And so there was no way you could use the Tian's criterion. But now, because of all the developments we have had with the different invariants, it's been proven by Chelsov, Park, and Won in their paper for this particular exception. The way they went with proving this is by showing that the delta of this is greater than or equal to 6/5. So it's just an estimate here, but that's good enough for us because this is greater than 1. And from the thresholds I had given you, this means it's K-stable, which implies it's K-polystable, and therefore there exists a Kahler-Einstein metric. And so, just to give you the whole picture in just one sentence, when I is 1, there always exists a Kahler-Einstein metric. So this has been done. And now for I equals 2, what did we know? Even before we started our work, we knew that by the works of Boyer, Galicki, Nakamai, Chelsov, Park, and Shramov, we knew the results for many of the series. So many of both the infinite series as well as the sporadic ones. We knew that there exists a Kahler-Einstein metric. In all of these cases, it was the existence. So they came up with the conjecture that basically stated that, okay, if my index is 2, then it looks like there's always going to be a Kahler-Einstein metric. But this was disproven pretty recently by In-Kyun, my collaborators, basically, so and Won in their work. So basically, they gave 6 different hypersurfaces for which there does not exist a Kahler-Einstein metric. And this is in the case of index 2. Just for lack of time, I'm not writing down what the 6 are, but if I'm not mistaken, there are exactly 6 of them. So, which again, so this proves the conjecture that when I is 2, there's always going to be Kahler-Einstein metric. But this gave us an idea of, okay, so it's not going to be the case, but we had the rest remaining for us to prove. And this was our first work. So I thought instead of me writing it down, I will give you the exact result. So this is what we had proven in our work. So this is index 2, our work. and this completes it for index 2. Yeah, so basically in the cases that we did, which were the only ones remaining, we show that the Kahler-Einstein metric always exists. So this completes index 2 picture, and we have a very similar picture for index 3. So again, Boyer, Galicki, Nakmaya had already done it for many of the sporadic cases. And was also done by Chelsov, Park, Shramov into 2010 later. So with whatever was remaining, we managed to prove the existence or the non-existence. So let me again give you just the results. So this was again our work. So this is index 3, our work. But of course, this is not the end of it. There's some more. Yes. Okay. So this is what we have at the moment. And of course, for the higher indices, there's still a lot more to do. But I thought I'll give you just a picture of how these computations go. So let's take one example from index 2. I thought it would be interesting to do this because I don't know if I can write on this. Yes. So this was done using delta from Abban-Zwang theory. So for all the formulae I had written before, I thought it would be interesting to show you how the computations go there. And then for this, in these cases, for this we used beta. So maybe if I have time, I can show you how that goes. But for the rest, we used LCT computations to do it. So again, I have an example there as well to show you how that computation would go. So let me try to do all of them in the next 15 minutes, just to give you an idea. So index 2, the example I have is of degree twice n plus 3 in weighted projective space P1, 2, n plus 2, n plus 3. Say I'm giving it coordinates x, y, z, t. And let's say the polynomial that defines my S is given by t square plus z square y plus the rest of it. How did I come up with this? This is very easy. So you just need to write down the monomials that would give up this degree and suitable coordinate changes to then show that any such surface can be written in this way. So okay, so we have this to be the polynomial that defines the surface for us. Now, what are the singular points? There are going to be some singularities in it. So what are the singular points? We have a couple of them. So when n is even, because your n is anything greater than or equal to 0. So when n is even, what do you do? So it's the points are pz. For me, pz is when z is 1 and the rest are 0. So this is of type 1 over n plus 2, 1, 1. And I have two more points, which are basically of this form for different values of alpha, but it's of type 1 over 2, 1, 1. And similarly for n odd, I have three such points. I have pt, q1, and q2 primes with similar types. So this is of type 1 over n plus 2, 1, 1, and this is of type 1 over 2, 1, 1. So once we have this, let's try to compute delta of S. The objective is this. So let's take a point on the surface. So I'm going to do this using local analog. So we're going to compute delta P for every P on the surface. So let's take a point on the surface. The first step that you need, let me go back to the definition I had written earlier. So just so that you get it. So we take a point, we next need a curve, which is on the surface, but it's not just any curve. What do we need? We take a point, we need a curve on the surface that contains the point. So we basically have a flag here. So we have a point, we have a curve, and we have the curve in the surface. So we need to choose such curves, which is why it might be wise to now split it as different cases. So let me say my point that I take on the surface is lying on Cx. What is Cx for me? Cx is the hyperplane section given by x equals 0 intersecting with my surface that I have. So I'll just 2 times it. This is my curve. So now the first case I do is if I take a point on Cx, let's now compute delta p. So now if you notice the points of singularity, they all lie on your curve Cx. And if I was to write down these coordinates, you would see it's something very similar. So here, these are just 0, 0, 1, 0 alpha, and this is just 0, 0, 0, 1. So of course, all the points are lying on x equals 0. So when I say point on Cx, you're going to have 2 different cases. So you're going to have P to be a smooth point, and you're also going to have P to be one of those singular points. Let's try doing the smooth point quickly. So you're looking at the divisor minus Ks minus UCx. And because the index is 2, you're going to have 2 times Cx minus UCx because the weight on x is anyway 1. So this is nothing but 2 minus UCx. So this is, you can immediately see that it's effective when u is less than or equal to 2, which gives you that the pseudo-effective threshold is 2. So now you need AS of your curve Cx, and you need S of your curve. AS is 1 plus the order about the point when you have a birational morphism. So this is just 1 because you have not taken, so you're not working anymore on, like you're not working above your surface, you're working on your surface. So the divisor you've taken, you're looking at curves and on the surface S, which means there is no relative canonical here, and which is precisely why your order here is just 0 trivially, and so your log discrepancy is just 1. And then now when we do just this computation, which is 1 over ks square, 0 to your pseudo-effective threshold, volume of your minus ks minus ucx du. So we need ks square, and so ks being 2cx, you need what cx square is. And so we have a very similar Bezout type intersections for weighted projective space. So this then tells you that your cs square is 1 over n plus 2. And so your kx square is 4 over n plus 2. So when you do this computation here, you'll end up with a 2 over 3. And so your as of cx by ss of cx would be a 3 over 2. Okay, so this is fine because if you remember, my delta p was bigger than or equal to the minimum of 1 over ss of cx in our case, and then a of ep over this funny number. So this is what we now have to do. So okay, so now if my point is a smooth point, then we are okay because my a is still just 1. My s is what you would need to do. But for a singular point, I thought this might be more interesting for you to see how it would look like. So if my point was just pz, which was 0, 0, 1, 0, and I said it was of type 1 over n plus 2, 1, 1, I first need this. And this is nothing but 1 minus m minus 1 over m if my p is given by a cyclic quotient singularity of this form. So this is Shakurov's result in 3-fold log flips. And so in our case, because m is just n plus 2, this is going to be 1 minus n plus 2 minus 1 over n plus 2. So this is just going to be 1 over n plus 2. And so now when we do S, when we have to do this computation, this is very straightforward. So 2 over minus ks square, 0 to your threshold, h of u du. If you remember what h of u was, which was a very, very long thing, so you had some positive part intersected with the curve, order of the negative part along your point, plus the volume of the positive part restricted to the curve minus v dv. So this is simple in our case because, okay, what is p of u and n of u? That's exactly what we need. So let's look at the divisor. This is 2 minus u cx. And we're looking at u only from 0 to 2. So this divisor is effective. So when you want to check neftness of this divisor, it's enough to just intersect it with the curve itself. So 2 minus u cx dot cx is just 2 minus u over n plus 2 because we already knew what cx square was, and this is always greater than 0. And so we know that my divisor is already nef. And so from the Zariski decomposition that I had before, so you had a p plus n, my p is already my d. So my d is already nef, so my n is 0. Which means in my h of u, this is going to be 0 because there is no negative part for us. And so this is a very straightforward computation now. So it's just 0 to 2, 0 to infinity, volume of the positive part restricted to cx minus vp dv. But what is this? So we have 2 minus u, cx restricted to cx, so it's cx square. So it's 2 minus u over n plus 2. So this is 0 to 2, 0 to 2 minus u over n plus 2, 2 minus u over n plus 2 minus v dv, du. And so when you do this computation, you get something of this sort. And so the second number in your inequality, so this was a 3 over 2 for us already. So this is a 1 over n plus 2 over 2 over 3 times n plus 2. And so this tells you that your delta p is at least 3 over 2. But this is only in the case when my point is on cx. But it's just giving you an idea of how these computations, so this is something that you can explicitly do with brutal force, you can just do this. So this is for any point on cx, we have shown that delta p is always greater than or equal to 3 over 2. But you can do this for every other curve. So now when you take another point on the surface, which is not on cx, now you immediately know if my point is not on cx, what do you do? Because now you need a curve. So because I know my point is not on cx, I know my x coordinate is going to be 1. So it's some yzt. Now you look at the equation of S and you realize that you can always have a curve so this would be the curve through which on which your point lies, because this is, so you're working with 1, 2, n plus 2, n plus 3. So y having weight 2 and x having weight 1, you always have this curve on your surface. So because you know your point is not on x anymore, you know your coordinate on x is 1. So any such point is going to lie on any such curve for some mu. So now you have a curve. And so you need to do the same process again and do the same sort of computations again to then see what delta is. And in the end, we got this delta to also be somewhere around 3 over 2. And so in total, my delta was always greater than 1. And so we showed that it was k-stable. So this is one way, but I think I don't have time anymore to show you any of the other examples. But this is very similar to how you would do, like when you do LCT computation, it's just brutally just looking at the equation of the surface that you have and doing just by definition of trying to find out what the low-canonical threshold is of it. And then using Tian's result is pretty much how you would go about using LCT. And beta is something very similar too, because beta is nothing but A minus S instead of it being A over S. And so that's another invariant that you could use. But I think I'll stop here just to ensure I'm still on time.